if the mass of the initial star is less than 8 times the mass of our sun, then it will actually follow this path, actually the path above. It will go through a red giant planetary nebula and forms a white dwarf. And when the mass of the star is greater than the 8 times the mass of the sun, then it will follow the bottom actually panel, that is massive star going through red supergiant and one core full of supernova. Then depending on the actually initial mass of the initial star, it will be a neutron star or a black hole. Now, just a little bit about this fusion process. So, first process is the high hydrogen burning, because all main ingredient of all stars actually is hydrogen gas. So, if you want to produce a helium nucleus, then 4 hydrogen nuclei should fuse and then produce a helium nucleus. So on the left hand side, what you are seeing, 2 hydrogen nucleus actually fusing and producing a deuteron. Again another hydrogen nucleus fuses with the deuteron, produces a helium, to fuse, produce a helium nucleus, where we have 2 protons, 2 neutrons. Now, this environment is hot, actually, while this burning process is going on, is hot. But still, it is not that hot that the energy of the protons will be enough to overcome the Coulomb potential or Coulomb energy. So, then, because if we do not overcome this proton-proton repulsion, then there will be no fusion. But in quantum mechanics, you know there is one mechanism called tunneling, and through this process actually, through this quantum tunneling, is to though this energy of proton is below the Coulomb energy barrier, it will fuse and produce actually this helium nucleus. So another process actually in this case is the carbon, nitrogen, oxygen cycle. In this case actually carbon acts as a catalyst. Now I said that main ingredient of star actually is hydrogen gas, but still it is contaminated with little bit of these heavy elements like nitrogen, oxygen, carbon, etc. Now here you can see that in this case actually this carbon actually fuses with one hydrogen, produce nitrogen 13, then nitrogen 13 in unstable, it decays, then it gives carbon 13, again carbon 13 fuses with another hydrogen, produce nitrogen 14, which is a stable nucleus, and then again nitrogen 14 fuses with another hydrogen, produce oxygen 15, which is again an unstable nucleus. So it goes through beta decay process, and it produces nitrogen 15. Again, it fuses with another hydrogen, produces helium, and carbon. This carbon nucleus comes out of it, because it is just else going this reaction to produce helium 4. Okay, so this is more or less about the hydrogen burning, that is the main burning stage of a star. Now, here in this diagram, it is shown pictorially various stages of burning process: hydrogen, helium, carbon, neon, oxygen, silicon. And after each burning is actually is over, there is an arrow. That means there is no energy production, so gravity actually compresses the whole star, and the central density and temperature increases. So that provides actually right kind of platform for the next stage of burning actually. because you need higher temperature to produce higher, heavier element through this fusion process. At the bottom, these various temperature at different stages of burning are shown. Similarly, the density. So at a most of the time, star spends in this hydrogen burning state, and this temperature is of the order of 10 to the power 7 or more, and density 5 gram per centimeter cube. And the time scales for the burning stage at the bottom, actually, you can see it is almost 10 to the power 7 years. Now, if we go to heavier element, for example, carbon, we can see that this time scales for this burning is 600 years. It is just decreasing. Time scale is decreasing. On the other hand, the temperature and density is increasing at the center of the star. When silicon burns into iron nucleus, the central temperature is of the order of 10 to the power 9 degree Kelvin, and density is of the order of 10 to the power 7 gram per centimeter cube. And this silicon burning to iron actually completes in one day. So this is a big problem. Just looking at a star, we cannot say which star is going to be a supernova. So this is a very fast process in the later state actually. And after the formation of iron, we could generate energy actually. Energy, as I told you, is energy production is very important thing for the star to keep it in stable equilibrium. But after the formation of iron, there will be no production of energy, because we cannot use two iron nuclei and produce energy. Rather, we have to supply energy to produce two iron nuclei. So this can be seen from this plot actually. On the left side, it is how this various elements synthesized during these various burning stages are layered inside this iron. Not only iron nuclei, there are nickel, cobalt, etc. Those together called iron group nuclei. So this center is called the iron core. Outside, we can see that layer of silicon, oxygen, neon, carbon, helium, hydrogen. So this structure is like an onion. That is why it is called a cosmic onion. If you peel it from outside, and you will see different layers as you go inside it. Now on the right hand side, this energy, binding energy per particle is shown as a plot of mass number. So we know that this binding energy actually peaks around iron nucleus. That is why we cannot actually generate energy just fusing iron nuclei. Okay, so after this formation of this iron core at the center, now many interesting processes will happen inside at this actually inside this iron core. So what are these processes? First thing, we ask that there is no production of energy. That means this core is then, or the whole star is unstable, because there is nothing to balance this gravitational force. But we know Chandrasekhar actually showed that if there is degenerate electron pressure, it can actually balances the gravitational force and stabilize a particular kind of compact object, which are known as white dwarfs. Now, this Chandrasekhar mass actually formula is very simple. It is, the final expression for it very simple. So it is proportional to electron fraction square, and it will be multiplied by just solar mass, which is missing here. Now, what is electron fraction? So we are considering iron core. Look at one iron nucleus. So we have in the or iron atom, we have in the nucleus we have 26 proton and total 56 neutron plus protons. And if we consider atom, then equal number of electrons for these 26 protons. Now, if we divide this proton number 26 divided by 56, we get this electron fraction. And if we plug it, we get a value for this Chandrasekhar mass as 1.44 times solar mass, or mass of our sun. Now, the question is whether the electrons actually, whether these electrons in the iron core can actually give some sufficient pressure to balance this gravitational force to prevent the collapse. But we'll see that that is not possible, because it is such a denser medium in the core actually, that this electron will be captured by various nuclei present inside the core. For example, at the end actually, one such reaction is shown. One nucleus A, n number of neutrons, Z number of protons, actually capturing a electron, producing a nucleus with n plus 1 number of neutrons, Z minus 1 number of protons and neutrinos. So that is this capture. Due to this capture actually, electrons are depleting very fast from the system, and as a result this electron pressure will diminish in the system. So electron pressure is not a viable mechanism to stop the gravitational collapse. Then what will happen then? So core will at the center actually will be more compressed due to this gravitational force, and density will increase. When the density actually is about 2.7 times 10 to the power 14 gram per centimeter cube, then all these nuclei will actually will be crushed into their fundamental constituents, that is neutron proton, and these neutrons protons will form a uniform nuclear matter. Now, if gravity further compresses this matter, then neutrons or protons will come closer. But from nuclear physics actually lessons, we know that nuclear force is short range repulsive and strong range attractive. So when neutrons or protons are coming very close in the touching configuration, then there will be a strong repulsive force, and that will resist actually this gravitational collapse. As a result, a shock wave will be generated at the center of the core. So it is shown in the bottom actually diagram. So all these arrows showing this shock wave is propagating through the mantle of the star. Mantle means, if you try to remember that onion structure, all these layers of elements were there. So this shock wave will pass through all these layers of elements and through this explosion mechanism, through all these layers into the universe. And this will be a supernova explosion. And all these elements actually created, actually they are related for our life. So that is why generally supernova explosions are called supernova explosions actually. Yeah. Generally it is called, we are the gift of the supernova explosions. So this is more or less the supernova explosion mechanism. I just go back one slide. Yeah. So when I told you that this nucleus is capturing an electron, that means its Z number is decreasing, N number is increasing. So here from this, here is a clue why the end product will be a neutron star, mainly made of neutrons. So at this stage actually, slowly all these elements actually becoming more neutron rich. That is why the end product will be a neutron star. This is this is a clue. We will see it later. Now, come back to this supernova 1987A event. Essence, here this nomenclature, Essence stands for supernova. 1987 is the year of this explosion, and A is the first event of that year, that is why A. Second event will be denoted by B, so on. Now, there were some round-the-clock neutrino observatory working at the time of the explosion. One of them was in the mountain Kamiokande in Japan. So what is this detector actually? These are huge tank full of water, H2O, and there are this, then you have scintillator detector which capture radiation photon. So when a neutrino passes through this, tank of water, so what it does, it actually interacts with the proton of the hydrogen nucleus, H2O, so hydrogen nucleus, each hydrogen nucleus has a proton. So at the bottom, this antineutrino interacting with a proton, then it is giving positron and neutron. And this positron is a charged particle, it propagates. Actually, when charged particle propagates, it radiates, which is known as Cherenkov radiation, and those are captured by this photon detector or photomultiplier detector. At the bottom are shown the energy of these neutrinos as a function of time. So you can see, if you look at this, time is given in seconds. So we have seen something like 19 events up to 11 seconds. But if one theoretically calculate this number, it comes about 10 to the power 57 neutrinos were emitted from the core of this star in supernova 1987A. But we could only detect 19 events. So it shows that how weakly interacting is this particle. It just passes through our body, it passes through anything actually. Very difficult to detect. Okay, so something is happening right now about the supernova 1987A. This is again in discussion. What you see, this is the remnant of the supernova 1987A. This year, beginning of this year, some astronomers are actually observing it, and they found that inside this shown here, nothing but a dust, something is inside it. So we are looking for this neutron star over the last 33 years or so, but we could not find anything like that. But after this hitting of this dust actually surrounding this neutron star, people are actually very hopeful that there could be something. Either it is a neutron star or a black hole. Most possibly, there is a paper last week in Astrophysical Journal. They actually said that most possibly it is a neutron star. Okay, so I now come to some of the historical supernova events in our galaxy. Hello, can you hear me?
Yes, sir. No problem, sir.
Hello, can you hear me?
Yeah. No problem, sir. You are audible now, sir.
Only thing is my slide is not working actually.
Oh.
Okay, fine. I'm back to the slide. Historical supernova. One is Crab Nebula. It was observed in 1054 years in that year. And another is observed Kepler supernova. It was Kepler himself observed that in 1604. Now, in this Crab Nebula at the center, there is a neutron star. It is known as Crab. This is crab pulsar. So I will come to that. What is a pulsar? Now, what you can see, because these two, if you actually take the difference of these 2 years, actually, so you see that it is roughly 450 years for the occurrence of a supernova in our galaxy. So there should be another supernova due in our galaxy. What could be that supernova in our galaxy? So people are thinking about this particular star, Betelgeuse. Actually, it is a very very bright object. You can, without a telescope, you can see it in the constellation Orion, and this has a mass of 15 times the mass of our Sun. It scientists are saying that it has entered into the red supergiant phase. So the distance is 430 light years. So we are seeing that light actually. When we are seeing it as a red supernova giant stage, actually it might have entered into the carbon burning phase. As I told you, carbon burning phase means it completes in 600 years. Very fast things actually. So things are going on very fast there, might be. And this is actually, it is a hot topic. This is our next probable candidate for a supernova event. Now with this, I come to about this neutron star business. This is more or less about my supernova things. I come to this neutron stars things. So here you can see some of the visionaries who actually talked about a neutron star before the discovery of a neutron star by astronomers. So one of them is Lev Landau. He wrote a paper in 1931 before the discovery of neutron. As you know, that neutron was first discovered in 1932 by James Chadwick, and Landau's paper was published 2 days after the first publication of the discovery paper of neutron by Chadwick in Nature. So you can see it is coincidental, though Landau wrote that paper quite earlier. And the other two, actually, they predicted in 1932, made some predictions. I will show you that prediction. But it is after the supernova, it is after the discovery of neutron. Okay. So this is the paper of Landau who wrote. You can see on the right side when it was written, 1931, published. He had no idea of the discovery of the neutron when his paper was published or when he did his thing. So what he said that in simple terms, neutron stars are he did not talk about neutron stars, he talked about compact object is a huge bag of nucleus. So that was his that was his predictions. A giant nucleus, a compact object as giant nucleus. Precisely, this was his statement. We will see that later. And the other two astronomers in 1932 in a meeting in Stanford, and they said, Bardet and Zwicky, that I just read this last sentence actually. With all reserve, we advance the view that supernova represents the transition from ordinary star into neutron star, which in their final stages consist of extremely close-packed neutrons. It is just, only visionaries can make this kind of statement or write this kind of paper. Yeah. So this is the statement they made at that time, actually. Yeah. So next is the discovery of the neutron star by a lady, Jocelyn Bell, in 1967. So here is Jocelyn Bell. What you see, what they discovered is a pulsar, and she is actually standing near to this dish, that is a radio telescope. And what is a pulsar? Pulsar is a neutron star with very high surface magnetic field. This high means magnetic field is of the order of 10 to the power 13 Gauss, which cannot be produced in the terrestrial laboratory. And it is rotating very fast. So think of in your electrodynamics class that a moving charge produces, or a moving magnetic dipole moment produce radiation. So if we consider this pulsar as a just rotating magnetic dipole, then it is radiating, and this is similar to lighthouse effect actually in the cosmos. And this radiation is when coming to us, actually to the observer on the Earth at a different time interval, and that is the actually the period of the pulsar. So pulsar is very good clock. Their spin period is very precisely known nowadays. So this is more or less about this pulsar. And you can see on the left bottom, actually, there is some graph actually done by Jocelyn Reed at that time, because, yeah, what you are seeing that when there is a pulse, there is a peak actually. So this peak actually, there are small peaks, do not consider them. The big peak you consider in every 1.3 second period actually. That pulsar had a period of 1.33 seconds. Every 1.33 seconds there was a peak, and she noticed it, and then there was a paper. And the unfortunate thing is that her supervisor, Anthony Hughes, got the Nobel Prize, but she did not. But she was very humble to say that I was just a graduate student, so there is no actually, no way a graduate student could be given a Nobel Prize. But nowadays, when graphene was actually discovered, we know that a postdoc was given a Nobel Prize. So that is not the thing. Maybe it is more than that actually. Okay, so I talked about radio telescope. So come to this. Here is one such radio telescope. You see here. This is our own radio telescope, giant meter wave radio telescope, very near to Pune, and it is made in India actually. It is this instrument was made by famous radio astronomer Professor Govind Sarup. He is still alive at the age 91 plus. He lives in Pune. So it is a fantastic instrument. You are seeing just one dish actually. There are 30 such dishes. So if you get any chance, you can go there and yes, just and get a feeling of it actually. Now, neutron star was discovered in 1974 and 1967. Now in 1974, two scientists, R. Halsey and J. Taylor, they actually they discovered first binary neutron star system. In this binary, one of them is on the left object is actually a pulsar, and the other one is a neutron star. So this is fascinating thing, and they are moving around each other actually, and this is a Halsey-Taylor pulsar. Actually, in 300 million years later, they will actually come to each other and collide. But when they are rotating around each other right now, they are shrinking their orbit actually, and they are coming to each other. And as a result, what is happening? So one can estimate, because these objects are actually, these individual objects are also radiating not only electromagnetic waves, they are radiating gravitational waves too. So one can actually indirect measure the gravitational wave actually from this studying this kind of neutron star binary system, particularly this Halse-Taylor. So you can see here. So what is shown here is cumulative shift of periastron as a function of ER. So all these dotted points are the observed point, and the line actually what you are seeing here is this is the prediction of the Einstein general theory of relativity. So this shows that this decreasing shift of periastron actually time is due to this emission of gravitational waves, and this is actually the this is actually was the first indirect observation of gravitational waves, but direct gravitational waves was observed in 2017 when two neutron star collided. So here, this particularly, as I told you, that first neutron star was observed in 1967, and two neutron stars collided and produced direct gravitational waves in 2017. So this was actually in the golden jubilee year of the first discovery of a neutron star or a pulsar. So here what you see, three plots actually. On the top you see the two detectors in the top and middle, LIGO detector, one situated at Hanford, another is located at another location, that is Livingstone, and the last one at the bottom is the Virgo. This is located near Pisa. So you can very faintly actually see this signal, just before the merger. So what is happening is they are going close by, they are rotating or spiraling around each other, and you get that signal. And this signal is best noted in the middle figure. And when the signal is maximum, and because it was recorded for almost 100 seconds, around this, when this maximum, that means it is approaching towards the merger actually, when these two merges. And as a result, this gravitational waves were produced and they were detected from the Earth. And now I just, So a neutron star, this is a schematic diagram of a neutron star. And on the right side, a cross-sectional view of it. So what you see here, outer crust made of nuclei. In the inner crust, it is also made of nuclei, electrons, and free neutrons. In the inner, the difference between outer crust and inner crust is that nuclei in the inner crust are more neutron rich. So neutrons cannot be bound inside a nucleus, so they come out of this nucleus. So those are free neutrons, and these free neutrons can actually, they are fermions, they can form Cooper pair and also superfluidity. And below this inner crust, you have the this core where you have uniform matter of neutron proton, and in the inner core there are many other possibilities, actually various possibilities people talk about, not only neutron proton but also Bose condensate, quarks, heavier strange baryons which are known as hyperons. All these things can be could be possible at the very interior of a neutron star. And this is so far all these masses which are observed until 2014. we have so far actually discovered or measured masses of neutron star and discovered neutron stars of the order of 3000, and in most cases we could measure these masses very accurately. And at the bottom you can see the heaviest neutron star mass measured so far is 2 solar mass, which has a very small error bar actually at the bottom, and almost at the just below this cyan color actually band. Yeah. So now it is a common agreement that neutron stars are very heavy, which has a mass of 2 solar mass. Now, we have these are the various actually observatories which are already, some of them are functional, some of them will be functional in this decade. This is James Webb Space Telescope. So this is a optical telescope actually, just like it will be more powerful than Hubble. Then we have this millimeter wavelength actually, this ALMA observatory. There will be another X-ray mission, Athena, in space for the study of various compact objects. And Cherenkov telescope array, it is not for the study of neutron stars, but it is for the cosmic ray study. But one thing I should mention, this square kilometer array, where India in very big way involved, and this will be the most actually powerful radio telescope in the universe when it is operational, the later part of this decade. So this neutron star, not only actually they are detected in radio waves, they can be detected across the electromagnetic spectrum through X-rays, gamma rays, all this radio waves, using all this. So last 2 slides, I am done almost. This is square kilometer array, which is now just being built. This will be co-located in 2 places, one in South Africa, which is 800 kilometers north of Cape Town. Another, and this will be mainly made of dishes actually. I showed that it's like our GMRT dishes, but this actually technology is something different compared to our GMRT. And the other location is the Australia, which is 800 kilometers north of Perth. So only in this place actually only this is a desert. Only 100 people live. So generally we need a radio quiet zone for the study of this kind of object in radio, using radio telescope. Otherwise, all these television signals, radio signals, they can interfere with this cosmic signals, and that will create a problem for us. That is why people go to actually to places where population density is very, very low actually. So in this Australia, in this case, this detector are actually dipoles actually. Earlier days in our TV antenna, you have seen that dipole. It is very similar to that actually. So this many 130,000 dipole antennas will be distributed over 80 kilometers actually. Yeah. So with this, I just end saying that there is a great time ahead in science for the younger generation. You can, if you join all this in any one of this project, India will be actually benefited from your contributions. So think about it. Thank you very much. I thank the organizer for this for giving me this opportunity. And as I told yesterday, this talk is dedicated to my junior, Devrupa Chakraborty. Thank you.
Thank you, sir.
Thank you, sir, for this beautiful lecture. Now I will request Professor Devadesh Bandyopadhyay to take the chair and introduce Professor Mehdi Kalam.
Oh, Mehdi Kalam is giving the talk?
Yes, sir.
Okay.
There, from audience,
If there are questions, actually.
Yeah.
Questions. Mehdi, can you, just.
One from Dr. Shatabdi Ghosh.
Yes,
She's
what is the
asking,
question?
what is the function of a black hole in the galaxy?
The function of a black hole. So
I think she might be asking for supermassive black hole at the center. I think. Maybe.
okay, the black hole has lots of functions actually. It generates energy and keeps going this universe. Yeah, these are the things. But the supermassive black holes are good also for us. The next generation gravitational wave detectors, we will be able to detect gravitational waves from those things. Yeah.
Sir, one more question from Obhinanda Chakraborty. She is asking, how can we detect neutron star within supernova? And another is how did the magnetic field of the pulsar?
Okay, just first question, Obhinanda, how we can detect the neutron star.
Within supernova.
Detect the neutron star. Okay, so if it is a pulsar, there will be a pulsar radiating, and if those pulses are coming towards the Earth, we can detect it. So there is no issue with that. But generally, after the supernova explosions, there is, as I told you, that lots of actually elements are thrown into the galaxy. Actually, what we call dust, and because of that dust, we could not do it using any kind of optical measurement or the X-ray measurement of that particular. If there is a compact object in that supernova, we cannot do that. Now, just in this year, actually, the group actually which studied the interior of the supernova and predicting there could be a neutron star, what they did using millimeter radio wave actually, and they are seeing that there is a blob which is being heated. So this heat should come something inside. So there must be something like one neutron star, which is actually giving energy to this dust just outside. So another 1 or 2 decades it will take to settle this dust outside it. We can measure either using X-ray or optical. We could see. If it is a pulsar, then definitely you could see it earlier actually, because electromagnetic waves cannot be actually hindered by all these dust things. Yeah. Okay, next question. What is the other question you said? Yeah. What is that other question? I forgot.
Yeah.
Can you tell me?
Yeah. Other questions is that how did the magnetic field of the pulsar was measured from radiation?
Oh, okay. So there are various ways to measure it. First thing, as I told you, if you take it a dipole model, that is a pulsar is a dipole actually. For example, I mentioned about Crab nebula. So there is a pulsar, and this pulsar is rotating actually, and it is giving energy to this nebula actually. And this is coming at the cost of the rotational energy of the pulsar. Now, if you there are the energy loss actually due to this magnetic dipole model and this the illuminated energy of the pulsar, this crab nebula, this is a well-measured quantity. And one more thing goes into this picture is moment of inertia, which is not yet very clearly measured so far. But if you take it 10 to the power 45 grams centimeter square, then one can actually equate this energy loss due to this dipole magnetic radiation and energy which is gained by this nebula. Gain energy is a known quantity. From there, actually, on the left-hand side, this loss energy will involve your magnetic field. From there, you can easily calculate the magnetic field. And there is other ways to measure it. There are cyclotrons lines, actually, which are coming from the pulsars. And if you measure those, sorry, not cyclotron, cyclotron lines, if you measure, observe those cyclotron lines, from there also you can measure the magnetic field. Yeah.
Okay, thank you very much, sir.
Thank you.
Okay.
So let me first just, stop the presentation. You share it. In the meantime, I will, introduce you to the audience. Okay, let me introduce Professor Dr. Mehdi Kalam.
Sir, you just exit your presentation, sir.
Yeah, stop presenting.
Yeah.
Okay, I am exited?
Yeah.
Okay, Professor Dr. Mehdi Kalam is a professor in the physics department of Alia University, which is located in Newtown. Very nice campus there. I have visited him several times there. And he is also the Dean of Science and Engineering faculty there. He got his bachelor's, master's, and PhD degree from the University of Jadavpur. Professor Kalam, by training, is a general relativist. He also has the expertise of working on neutron star, strange star, wormholes, thin wormholes. He will talk about this thing today. So, with this, without further ado, I invite Professor Kalam to deliver his talk.
Yeah. Can you hear me, sir?
Yes.
Oh, okay. So, good evening to everybody. First of all, I want to extend my gratitude to the New Arabic College Authority for giving me opportunity to deliver this lecture. My talk is Wormhole in Galactic Halos. At first, I want to explain lucidly that what is a wormhole. So you see here it is a doctor's photograph. One side is Sahara, another side is Newark. And one traveler, if one traveler wants to go from Sahara to Newark, if wormhole exists, then with a single step, the traveler can travel from Sahara to Newark rather than a hectic journey. Mind that if wormhole exists. So now, what is a wormhole? A wormhole is nothing but a hypothetical tunnel which connects two different spacetimes with a throat. So a wormhole has two mouths and one throat. So if the wormhole is traversable, then matter can travel from one mouth to the another by passing through the throat. It is a beautiful picture here. These are the spacetimes, and these red lines is the light ray. That means this is the geodesic curve in the spacetime. Any one traveler wants to go from this A to B, and this A to B is connected through a wormhole. So suppose a traveler wants to go from A to B and the light is starting at the same point. Now light has to go through this red line and the traveler is moving through this wormhole. So its velocity is very, very less than the velocity of light. So it obeys the laws of relativity. So the traveler will reach far earlier than the light comes to be. So in that way, this wormhole can be treated as a shorter path for interstellar travel. So this is another picture of interstellar travel. So this is Earth, and this is another galaxy. So through this wormhole, this interstellar travel may be possible. Now, the term wormhole actually first introduced by American theoretical physicist John Wheeler in 1957. The wormhole actually, what is the analogy of called it as wormhole? If you take an apple and a worm wants to go from top of the apple to go to the bottom of the apple, the worm has two ways. One is moving through the skin of the apple from top to the bottom. Another is worm can create a hole, go to top to the bottom. So a wormhole traveler takes the second one, is a shorter path, creating a hole to travel to go to top to the bottom. So that's why it is called a wormhole. A brief history of the wormhole. Actually, in 1916, Ludwig Flamm, an Austrian physicist, looked at the simplest possible solution of the Einstein's field equation. One solution is the Schwarzschild solution, famous Schwarzschild black hole. But Flamm realized that Einstein's equation allowed a second solution also, which is known as white hole. So black hole absorbs everything and white hole actually repels. So if we put a black hole one side and white hole other side, so black hole absorbs everything and white hole will be the exit. But Flamm can't explain where this may be possible. Actually, this idea was given by Albert Einstein in 1933, where Einstein and Nadal Rosen give that idea, which is known as Einstein-Rosen bridge, and that John Wheeler later called it as wormhole. So this is the picture of Einstein-Rosen bridge. Now, the wormhole has mainly two types. One is called Lorentzian wormhole, another is Euclidean wormhole. So Lorentzian wormhole actually deals with the general theory of relativity. We are dealing the Lorentzian wormhole, and the Euclidean wormhole are studied in particle physics. In 1962, John Wheeler and Robert Fuller actually published a paper showing that this Schwarzschild wormhole is very, very unstable. It is pinch off as soon as it forms. Not even light can pass through it. It looks like this one. Look at the very carefully. This wormhole, Lorentzian wormhole, is very much unstable. Why it becomes so unstable? So look at here. Here is the space-time is there. Another lower portion is there is also space-time, and this space-time has attraction to this throat region, and this space-time attracts this throat region to the upward direction, as well as the lower portion of the space-time attracts the throat region in the downward direction. So that's why this throat region is pinch off. So it is tear off here. So that's why it becomes very much unstable. But what will be our idea? Our idea is to get a traversable wormhole. So to get a traversable wormhole, we have to be a stable wormhole. So for that, the idea of Kip Thorne, mind that Kip Thorne got Nobel Prize in 2016 due to his discovery with the gravitational wave. So it is the idea of the Kip Thorne is that if we place an exotic matter at the throat, then in that situation, this exotic matter has a peculiar property. The property is that it has a negative energy and as well as is violating the null energy condition. So it repels the gravity. So it is not the ordinary matter, it is the exotic matter. So if we place here the exotic matter, then the wormhole becomes a stable one. How it becomes stable, I will explain. Suppose we place in this portion, throat region, we place the exotic matter. So then what happens in the upper portion of the gravity, this gravity, as this exotic matter repels gravity, so this gravity will repel the exotic matter in the opposite direction, and also the lower portion gravity is repelling this exotic matter in the opposite. So these two opposite forces actually balances to stabilize the exotic in the throat region. Now the question is, so we know that this exotic matter having the negative energy. Mind that this negative energy don't confuse with the binding energy. It is the mass energy. It is the mass energy. So exotic matter having negative energy. So it is quite fictitious, right? So wormhole is only the fantasy. So according to the Mad Fisher of Washington University, now he is in Victoria University, New Zealand, that the good news about the Lorentzian wormhole is that after about 20 to 30 years of hard work, we cannot prove that they don't exist. Because this wormhole has a strong background of general theory of relativity. It comes from the solution of the general theory of relativity. So it has a strong background. I just want to mention here that we know that in 2016 the gravitational wave was detected, but Einstein predicted it in 1916. Gravitational wave has a strong background of general theory of relativity because it is the solution of the general theory of relativity comes the existence of gravitational wave. But at that time the technology is not so developed that we can detect the gravitational wave. After 100 years, our technology now so developed that we can detect. So I'm telling that the wormhole has a strong background of general theory of relativity. So as general theory of relativity is true, so the wormhole solution must be true. So scientists are agreed that okay, to get the traversable wormhole, exotic matter is there, and for that now the scientists are trying to minimize this exotic matter, minimize use of this exotic matter to get the traversable wormhole, and it was done by Mad Fisher and Shainkar from Kharagpur IIT and Norris PRL physical revealed in 2003 that they traversable wormhole by using the minimization is violating the non-energy condition. So is it an impossible task to get this exotic matter? Not at all, because a possible source of exotic matter lies in the behavior of certain vacuum states in quantum field theory, as well as in Casimir effect. So we have experimental evidence of existing this exotic matter. And one of these is the squeeze quantum state in quantum optics, where we see that during the vacuum fluctuation, the existence of negative energy is there. So look at this diagram. Here is the energy density versus position. So here, this is for the ordinary light. Here we see that this is the energy density here is positive. So during the squeeze state, we see that here in this portion, look at here, in this portion energy becomes negative. Here this portion energy becomes negative. But as we know that the energy is conserved, so for that this portion energy actually increases to balance the energy conservations. So we see here energy at some point, at some particular position, that the existence of negative energy is there. So we have to develop the particular time. We have to catch that negative energy. That is the main point I want to mention here. That so existence of negative energy is there. Another is in Casimir effect. In 1948. Henrik B.J. Casimir showed that the two uncharged parallel metal plate, for after the vacuum fluctuation, he actually calculated that in this region the energy comes out as negative. Scientists are trying to get this in an experimental way. So 80% of this Casimir effect experiment till now is successful. So if 100% is successful, then in that situation we can get that. So what will be our aim? Our aim of work must be to get the sophisticated geometry so that we can get the wormhole structure. And if we get the wormhole structure and a sustainable traversable wormhole will get, then in that travel interstellar distances in very short time. So scientists are trying to get where is that exotic matter? Scientists are searching for that. So a numerous wormhole model, that's why, has been done by different scientists. We have one model, is that what I mentioned earlier, that a construction of the theoretical wormhole supported by the phantom energy. So we take the phantom energy as a source, acting just like a exotic matter. I just want to mention here, I am going to detail about that, how we can calculate and how we show that wormhole can be constructed. So for that, here we take a static spherical symmetric Lorentzian wormhole, which is mentioned in equation number 1. Here we see this metric, and here this FR is very important. This is called the redshift function, and that must be finite. And this BR is the shape function. This BR is the most important part, because this shape function actually gives the structure, actually particular structure of the wormhole. That's why it is called shape function. And to get the wormhole structure, we must have to follow these 4 conditions. We must have to obey these 4 conditions. What are the four conditions? For first one is that the redshift function, this FR, must be finite for all values of R. This means that no horizon exists in the space-time. Another is that the shape function BR must obey following the conditions. Here we know that the wormhole has a throat, so it must have throat radius, and that throat radius R at the throat radius R equal to R naught. R naught is the throat radius. B R naught must be equal to R naught, and B prime R, that means taking the derivative with respect to R, B prime R naught must be less than 1, which is called the flare out condition, and BR by R must be less than 1, R greater than R naught for outside the throat. And the fourth one is that the space-time must be asymptotically flat. BR by R tends to 0 for R tends to infinity. So these 4 conditions must be satisfied to get the wormhole structure. So these are the solutions. I'm not going to detail of that. From the Einstein's field equation, we can get the solution, and that 4 conditions are satisfied. So that's why wormhole can be constructed. Now, as I told that scientists are trying to get the wormhole structure. So there is a measurement of that WMAP measurement, from where we conclude that the 71% of our universe is of dark energy, and we all know that the acceleration of the universe actually due to this dark energy. So and cosmological constant is also a very important for this dark energy, and it can able to explain the acceleration of the universe. Einstein also have some idea that lambda has something common with the matter distribution. So that's why we are taking that this lambda may be a source of that exotic matter. Of course, here we taken this lambda as a variable one, and taking that we have shown that the wormhole may exist. Now the interesting point I want to mention here, that as I told earlier, that scientists are trying to get where is the existence of that exotic matter is there. So scientists are trying for that. So there is an important matter is always there, that is called the dark matter, and a huge amount of dark matter is there in the galactic halos. Now what is a galactic halo? A galactic halo is an extended, roughly spherical component of a galaxy which extends beyond the main visible components. Look at this diagram. So this is, if it is in a flat diagram, then this part actually nuclear bulge, and this is the disk, and the position of the sun is this one. So halo, look at here, the red circle here, the halos are this is the spherical. So halo is there. So it is very much visible for the spiral galaxies. So also in the Milky Way galaxy, it is another diagram is there. The Milky Way galaxy, these are the halo point. And most importantly, I want to mention here that the halo mostly made of the dark energy, dark matter, and this dark matter density actually drops off with the distance from the center of the galactic center. So it depends on the center, distance from the center of the galactic center. Now, how the concept of dark matter comes? We know that this galaxy have some rotations. So for rotations, we see that whenever a particle is rotating around some center in a circular orbit, so in that situation, that velocity actually needs some rotational velocity. So for the galaxy, where the gas and the stars are there, which are observed, that observed velocities of the stars actually plotted, and that plot gives this red curve. This is the measured velocity. That is the velocity, rotational velocity versus the distance from the center. This is the measured velocity. And if we calculate theoretically that the observed values of the star and the disk, visible star and the disk, then that calculation actually shows this red curve. So visible one gives the red curve, but the observed data gives this measured ones. So this was first actually inspected by in 1932 John Hendrik Wood. So there is that just if we consider for the star and the gas, these curves looks like this one, but the observed one is this one. So gravity provides the acceleration of v square by r needed for the star and the gas to go around in circular motion. The gravitational field of the star and the gas alone is not consistent with this flat rotation curve. As it is flat, so it is called flat rotation curve. So to explain the flat rotation curve, actually first Zwicky actually called that there must be some hidden matter in the halo is there, that is called the dark matter. And that dark matter actually provides the needed gravitational field and the mass required to match the observed galactic flat rotation curve in the galaxies. So our universe is made of only normal matter with 4.4%, and the dark matter is near about 24.6%, and rest one is the dark energy 71%. So as I told earlier that scientists are trying to get the exotic matters. So in 2014, Farooq Rahman, Peter Kufitik, and Shoibal Roy have given a wormhole model by taking the dark matter density of NFW, N for Navarro, Frank, White. Three scientists actually given that dark matter density model, and which is shown in equation number 1. They took that NFW dark matter density model as that dark matter as a source of the exotic matter, and they shown that if we take that dark matter density as a source, they shown that all the conditions of the shape functions are satisfied. So wormhole conditions are satisfied. So and minus r versus r. So here is cuts. So that means this is the throat radius. This is the throat radius here, and also dBdr it looks like this, and this is the very important one. Look at here, rho plus pr. So this is negative, so it's violating the non-energy condition. So it obeys all the conditions. So it's satisfied. It is published in Physical Journal C. In the very next paper, they shown the very important point that the NFW model, the observational data, says that the outer region of the galaxies, the observed part is well fit with the NFW dark matter density profile model. But inner region of the galaxy, central region of the galaxy is not matches. So Paolo Salucci is a dark matter specialist. He is one of the proposer for a model which is called URC dark matter density profile, universal rotational curve dark matter density profile, and shown that the central region of the galaxy as well as for the outer region, this URC dark matter density profile more or less matches with the observational result. So they took this URC model to explain the wormhole. They try to exit the possible existence of the wormhole in the center. And they successfully have shown that if this is the URC density profile model, and they successfully shown that by taking this, they can construct the wormhole. Most important point I want to mention here that this R naught is the core radius and rho naught is the effective core density. They took this value for the Milky Way, observed value. They took this for the Milky Way, only for Milky Way galaxy. They proved it for Milky Way galaxy. And these are the observational data, rotational curve data, and they use that. And this is one of the galaxies, curve. This is the observed one. And by taking this URC dark matter density profile and applied for Milky Way galaxy, they proved that it can construct a wormhole. And this is the BR minus R gives. This is the R naught is the throat radius, 1 kiloparsec. And it also obeys the violating the null energy conditions. I want to mention here that after publishing this paper in Annals of Physics, Paolo Salucci has made the press, and he declared there they are getting these interesting results, and which is published in many international newspapers, and it is widely spread. And motivating with this, my collaborator in Iran, Institute for Advanced Studies in Basic Sciences, I do this work when I went to Iran as a towards University Associates there. We are trying to do that they shown that for only Milky Way galaxy. So we are trying to get this result for why not for other galaxies also. So for that we take 50 different galaxies. So 25 taken from the dwarf galaxy and 25 taken from the spiral galaxy, massive spiral galaxies. And we took the rotational curve data for 25 dwarf and for 25 massive galaxies. And from there, we want to check whether that data, from that data, experimental data, we can construct the wormhole or not. And for this, we take a simplest dark matter density profile model that is called the singular isothermal sphere dark matter density profile. It's the simplest dark matter density profile model, singular isothermal sphere dark matter density profile model. We take this. So this is the as usual pattern. So this is the equation number 1. This is the SIS model. I want to mention here that this SIS model, the density depends on this K. This K is the velocity dispersion. And look at here, if we calculate for V square halo, and V square halo is calculated from the observed rotational velocity curve, and this V square halo comes out as 2K. So this V square halo can be calculated from the observed rotational velocity curve, and as V square halo can be calculated from there, so K, we can get the value of K from that, and that K has some contribution with the shape function. The shape function is dependent on this K. So by using this, we this is the data. This is for the 25 dwarf galaxies data, and this is for the 25 massive galaxies data. And by using this, we able to construct the wormhole. And look at here, this is for the dwarf galaxy. The dwarf galaxy, we see here this Br minus R, the throat radius comes out as 1 kiloparsec. And for the massive galaxies, that throat radius comes out as 10 kiloparsec. So this is very important. I want to mention later. So this is for the spiral galaxies 10 kiloparsec, and this is for the 1 kiloparsec. And also for the dwarf galaxy and for the spiral galaxy, it obeys, it violates the null energy condition. So we get the structure of this wormhole. So in conclusion, I want to mention here that the scientists are still not able to create the null energy violating exotic matter in the lab. So dark matter in the galactic halo may act like null energy condition violating exotic matter. And wormhole may be formed naturally with some astrophysical phenomena by taking this dark matter in galactic halo. So wormhole may be formed with some astrophysical phenomena naturally. So finally, I want to mention one very important point here also, that as I shown earlier, that the throat radius for the dwarf galaxy comes out as 1 kiloparsec, and for the spiral galaxy comes out as 10 kiloparsec. That indicates that these are the greater, these values are the greater than the horizon of the supermassive black holes present in the dwarf as well as spiral galaxies. So that indicates that implies that the throat region of the wormhole contains supermassive black hole and dark matter. So our result says that it contains the supermassive black hole and the dark matter. Of course, the wormhole in this situation may be a large one, and so it may be very interesting result. Of course, it needs further investigation, but our result says that. And similar type of proposal also given by K. Dimopoulos in quantum field theory, that for further reference for the researcher who wants to interested on that, they can stay. This ends my lecture. Thank you very much. I acknowledge again to New Alipur College Authority for giving me an opportunity to do this.
Thank you, Professor Kalam. So
Yes.
Questions from the audience? So maybe
Sir,
there is a question: what are the properties of dark matter?
What are actually that we don't know the properties of the dark matter, because this dark matter is not interacting with the electromagnetic force. So we only realize that there may be a dark matter, but as it is not interacting with anything, no electromagnetic, so light can't absorb it, and light can't reflect it. Only what we can say, we can feel that there in the LIC experiment, what happens in LIC experiment, if dark matter is produced in LIC experiment, so in that situation, what happens, we can see that the interacting with the there is a dark matter is produced with the collisions, and in that situation, what happens, the dark matter can't interacting with anything but taking energy and the momentum from that collisions. So if we analyze the LHC experiment and what is the loss of the energy and the momentum there, in that point of view, we can say that the energy and the momentum of the dark matter is there. So it is an indirect.
So next question is there any observational evidence of wormhole?
No. As I told several times, that till now we don't have any observational evidence, but scientists are trying to that, and our result is that we are trying to give that model, and from the observational data of the dark matter, we can construct that wormhole, and in that situation, this is the model is there.
Can you suggest any book on this topic?
In this topic, for the wormhole is a famous book of Matt Vischer is there. Okay. Yes.
What is phantom energy?
Phantom energy is kind of energy where the equation of state parameter is there. One is P equal to omega into rho. That value equation of parameter omega is less than minus 1. So that kind of energy taken as, it is one type of dark energy.
Okay. Does the wormhole or that throat can be used in time travel, or is it related to?
Yeah, of course, that wormhole may be used in time travel. I show the diagram is there where any traveler from go to A to B, and in that situation the traveler reach B rather than the light comes to B. So in that way, time travel can take place.
Are black holes produced by dark matter?
No, it is not. We can say that because dark matter, as I told earlier, that the dark matter has no interaction with the electromagnetic force. So we can't say that.
If one travel by wormhole, will time be dilated?
Will time be dilated?
Dilated.
Yes, of course, because in that situation, special theory of relativity is valid there. So no problem is that. So all time during the time travel, during a wormhole traveler, the special theory of relativity is valid there.
Okay, there is another question, long question, but you can reply it later in writing.
Okay, that's no problem.
Where dark energy goes?
Where dark energy goes, we don't know.
Yes.
We don't know. 71% of the universe is dark energy.
Okay, so there is no other question. Let us thank the speaker once again.
Okay, thank you, sir. Thank you.
So our next speaker is Andrew. Andrew is available?
Yes, Andrew is available, I think. I have to leave, right?
Yes, I am available.
You are available.
Yeah.
Good morning, Andrew.
Good morning. Thank you very much.
Okay, so let me introduce the speaker to you, Dr. Andrew de Benedictis. He is currently now associated with he is a faculty member in the Department of Physics at Simon Fraser University, as well as the Specific Institute for Mathematical Sciences. He did BSc from the University of British Columbia, Canada, MSc from the University of Windsor, and PhD from Simon Fraser University. So he is a specialist in quantum and classical gravity, mathematical aspects of field theories, quantum field theory of fields. He authored many research papers, review articles, book chapters, and he also wrote a book on quantum field theory. So his title of his talk is The Role of Quantum Gravity in Astrophysics and Cosmology. Without further ado, I invite Andrew to deliver his talk. Andrew?
Thank you very much. Just a quick check if you can hear me and if you can see my presentation all right.
Yeah, I can see your presentation. I can hear you.
Thank you very much. Thank you. So it is a great pleasure for me to be here. I would like to thank New Alipore College and all the organizers for this opportunity. I will be talking a little bit about the role of quantum gravity in astrophysics and cosmology. Something interesting about quantum gravity is it lends itself to the question of why is it needed? For example, let me just do one thing. I'm just going to change the presentation mode. Okay, can you still see? I just changed one.
Yeah, I can see it.
Great. Okay, thank you. So what one question one can ask is, why is quantum gravity needed? We don't hear about it much in the realm of physics unless one is in this field. So I will try to address that, and I will try to explain why it has some importance in astrophysics and cosmology, even though it seems like a bit of an esoteric subject. Then I will give some results, some of which I worked on, and many from other researchers, and I will conclude in the end with some concluding remarks. So first of all, let me just do a very, very quick review of Newton's law of gravity, which, as you know, is in Newton's paradigm, gravity is just a regular force. And here is an expression for the force of a static gravitational field. You have the material here. You integrate over the source. Then this expression here at the top, this expression here at the top gives you the force on the mass due to this distribution of material. And using Newton's law of gravity is perfectly fine for almost any study that involves gravitation. It is good for studies of stellar structure, galactic dynamics, planetary structure, and planetary studies in the solar system and things of that nature. But there is, of course, it's been supplanted by general relativity around 1915. And general relativity is a very interesting theory. One is it makes gravitation compatible with the special theory of relativity, which had been out since 1905. Newton's law of gravity had problems with special relativity. General relativity, on the other hand, is fully compatible with special relativity. Now, the equations for general relativity are quite a bit more complicated than Newtonian gravity. We can summarize it here. These equations, many of you are familiar with them, but these are essentially matrix equations with the indices representing the row and the column of the matrix. If one were to write out these equations in full, they would probably fill up about 100 pages. It can get very, very complicated. This thing R with the two indices, again, for people that are not familiar with it, this is called the Ricci tensor. This quantity here, R, I hope you can see my mouse scrolling here. This quantity R, maybe I'll write on it. This is the trace of the Ricci scalar. This is called the Ricci scalar. It's the trace of the Ricci tensor. The material that causes the gravitation, the information about that material is here in this T quantity, which is the stress energy tensor, which is a relativistic generalization of the stress strain tensor in materials engineering. Self is encoded in these quantities on the left-hand side of the equation. The real gravitational field is in this quantity at the bottom with these four Greek indices. This is called the Riemann curvature tensor. If the Riemann curvature tensor is 0, you have no gravity. If the Riemann curvature tensor is not 0, you do have gravitation. So that's where the gravitation is encoded. And this Ricci tensor is just a single trace of the Riemann curvature tensor. And then, of course, the Ricci scalar, you trace it again. Okay, so this quantum gamma, which you create the Riemann tensor out of, is called the connection. In general relativity, the connection is the Levi-Civita connection. This is sometimes called the Christoffel connection. It is created solely out of the metric and its derivatives. The metric gives you distances in space and time. So by taking, it is kind of generalization of Pythagoras theorem on a flat sheet of paper. And so just remember that this quantity G mu nu gives you distances, and by combining this G mu nu, this matrix here, and its derivatives in a certain way, you will get this Christoffel connection, which then you construct the Riemann curvature tensor out of. And so when you hear the words a curvature and connection, mathematicians start to think about, of course, a curved manifold with connection. And that's exactly what how general relativity describes gravitation. As Mehdi was talking about earlier, we now have a space-time, and it is some sort of curved manifold, and that free particles, meaning particles with no force on them except for gravity, but gravity is now no longer a force. What is gravity now? It is just the free particles moving just the free particles moving along the geodesics of this curved manifold. So think of some curved surface, and if a particle lives in some curved surface, it of course will not necessarily travel in what we call a straight line, a conventional straight line. And when this is what we see as gravity. So it's quite a bit different. It's not a force in the usual sense, this gravitation in the paradigm of general relativity. So curvature, how does one measure curvature? There's many ways, but one thing one can do is parallel transport a vector in a loop. And as you see on the left-hand side here, if you go around a loop, and when you come back, when you parallel, I won't go into the details of parallel transport, but there's a way to do this. When the vector comes back on itself, there is an angular difference, like we see here, then you have non-trivial curvature. The loop is living in on a manifold with non-trivial curvature. If, on the other hand, there is no angular difference, say the vector comes back on itself without a change in angle, then there would be no gravity. So this is one way to measure curvature. The physical way, of course, would be to measure what are called tidal forces, the tidal forces of gravity. But mathematically, it's equivalent to discussing what's called the holonomy, the angular holonomy of the vector upon parallel transport in a loop. So this general relativity is a completely different paradigm than Newtonian gravity, but it does make exactly the same predictions as Newtonian gravity when the gravitational fields are weak and the particles move with much less than the speed of light. And this is the bulk of the cases that one encounters. But then the question is, okay, well, how weak is weak? How weak of a gravitational force is weak, and where does general relativity become important? Well, actually, it depends how precise you want to be. For example, the gravitational field of the Earth is considered very, very weak by the standards of general relativity. However, if you want absolutely precise GPS coordinates on your cellular telephone, you actually need to take into account general relativistic effects, even though they're very weak. And if you want that super precision, you're going to need it. The perihelion precession of Mercury was known for a long time, that Mercury's perihelion, point closest to the sun, precesses a little bit. Very tiny amount that could not be accounted for in Newtonian gravity. Again, that gravitational field is considered weak, but we start to see general relativistic effects there. But these are small effects, and one can maybe perhaps not worry about them too much. But in most astrophysics, the scale at which general relativity becomes important is when you start getting to the neutron star scale, meaning gravitational fields in the vicinity of neutron stars or more compact objects. And we had a nice talk this morning, a very interesting talk on neutron stars. So I will review a little bit about what was said in that nice talk this morning. This Hulse-Taylor pulsar. You have one is a pulsar, as was mentioned. The other is an ordinary neutron star, I believe. And general relativity predicts that they should emit gravitational radiation. Gravitational radiation, of course, means that some form of energy. Energy is quite a tricky subject in general relativity, which I won't go into. But if you'll permit me to use the language of energy, that some form of energy will be taken away from this binary system in the form of gravitational waves. Here's a kind of a cartoon from Wikipedia. And of course, if you take away some sort of energy from two orbiting objects, their period should decrease. And here is a picture that we saw earlier this morning. And what we have here is the cumulative period shift, or the decrease in period over time, from about 1975 to 2005. The dots are the experimental results, and the solid line is the general relativity prediction. So general relativity is very good theory of gravity. And now we are starting to talk about in the strong gravity regime, because we are talking about neutron stars, and that's where it starts to become important. So we see it seems to pass this test very, very nicely. Now, something interesting about general relativity, and Mehdi talked about this in the previous talk a little bit, is the pressure. You'll remember he mentioned pressures in his talk. Well, as you can imagine, a neutron star is very dense. There is a lot of gravitational pull on this neutron star, trying to pull it inward. What is holding the neutron star outward is pressure, degeneracy pressure, things of that nature. But something about general relativity, which is quite different than Newtonian gravity, is that it's not just the mass density that produces gravity. It is that, you remember that quantity I called the stress energy tensor earlier. That has many things in it. The mass density is only one of many things that live in that mathematical object. One other thing that lives in that mathematical object is the pressure. And that means that the pressure actually creates gravity. So if you have a lot of pressure, as well as a lot of mass density, you're going to get a lot of gravity. And if the pressure gets too large, then the pressure, because it causes gravity, will also cause gravity to get very, very large. And that will cause the object to collapse because gravity is getting large, but that increases the pressure. So we run into a bit of an issue potentially. It depends. But what could happen is you create more pressure. That creates more gravity. That's going to create more pressure because gravity is collapsing the object. But if you're creating more pressure, that's going to create more gravity. And you have a possibility of a type of runaway reaction in general relativity, a possibility of this. This leads us to a concept which many of you have heard of called the black hole. Here's a picture, our first sort of direct picture of a black hole, which is a very famous picture now, down in the lower right there. So what happens if the pressure cannot hold up against the gravity that it is producing? Then you're going to get continued gravitational contraction. I like this phrase a lot. It was coined by Oppenheimer and Snyder in Physical Review. I should have put the year here. I don't remember the year of this publication, but I believe it was in the 1930s. A very nice paper by Oppenheimer and Snyder. And what will happen is you will get collapse, and this object will collapse beyond the point where its gravitational field is strong enough that even light can no longer escape. And this we call the event horizon of a black hole. And Mehdi mentioned this morning earlier about event horizons. So what is going to stop the collapse? If this thing is collapsing, pressure is increasing, it's going to collapse more. Well, there is no reasonable physics within general relativity and no reasonable equation of state that we know of that is going to halt the collapse. Of course, as Mehdi mentioned earlier, you can invoke exotic matter because exotic matter will anti-gravitate. That is certainly a possibility, but barring something exotic like that, there will be no reasonable physics that can halt this collapse. Where else does something like this happen? Well, a similar argument holds in the realm of cosmology. Cosmology is the study of the universe in its entirety. And those Einstein equations, those relativistic gravitational equations we discussed earlier, under reasonable physical assumptions, they predict a Big Bang right here. That means that if you follow the universe, the evolution of the universe, far back enough, you run those equations backwards in time, eventually you get a region of essentially infinite density. This is essentially a black hole in reverse. Okay. The black hole was collapsing down to a more and more dense object, and eventually you get an infinitely dense object with that type of black hole. That's called the singularity. If you run that film backwards, imagine running that argument backwards, then you have essentially the Big Bang. This is kind of like a little bit like the white hole that Mehdi had mentioned. So general relativity predicts under reasonable conditions that the universe started from an infinitely dense state. However, after the Big Bang, because we don't like infinities, mathematically we cannot deal with them, and physically they don't make much sense. But after the Big Bang, general relativity makes predictions, which to date seems to have passed pretty much all observations. Newtonian gravity, there are some papers on this on the archive if people are interested, but there are many reasons why Newtonian gravity is generally insufficient to describe the evolution of the universe. Overall, there are many, many places, of course, in astrophysics and cosmology, where Newtonian gravity is, of course, fantastic. It's perfectly valid. All right. So what the summary here of why we want to talk about general relativity is that we need general relativity in astrophysics and cosmology for neutron stars. Black holes, cosmological evolution, at least to some extent. And if you are interested in highly precision experiments, such as the precession of Mercury, or of course your GPS, or your frequency shift of photons, then even in the weak field regime, you're going to have to invoke general relativity, even if just at a perturbative level. Depends on the precision that you are after, as we discussed earlier. Now, let me talk a little bit about quantum gravity, which everything I've talked about so far has not involved quantum mechanics. That general relativity is a classical theory of gravity, meaning non-quantum, and it's a very, very good theory. But as we saw, it causes a little bit of a problem. There's the Big Bang singularity. What happens at that infinitely dense point at the start, what we think was the start of the universe? Well, what happens after the Big Bang? Okay, that's general relativity is very good for that. But we can't go before the Big Bang because of that infinity. So maybe quantum gravity will help us figure out what happened before the Big Bang. We also need, I won't get into this, but if anybody is interested, we can talk about it, the consistency between the gravitational field and the quantum nature of matter. Very roughly speaking, the issue here is that we know matter at a fundamental level is quantum. Matter is what gravitates. Therefore, to have a fully consistent theory at very high energy, we need to reconcile the quantum nature of the matter with the gravitational field that it produces. That's an interesting point. That's an interesting area of research. So let me talk very briefly about quantum mechanics before talking about quantum gravity. In quantum mechanics, this is a very quick review, that essentially the most fundamental statement, I think, in quantum mechanics is that mechanically conjugate variables do not commute. That means if you have a system, say a particle, and you have its canonical momentum, and you have its configuration variable, which is usually the position, and you take the commutator of these two quantities, p times x minus x times p. If they were if they behaved like I would expect ordinary functions to behave, p times x minus x times p would give you 0. But in quantum mechanics, the commutator is slightly non-trivial. Depends on this constant h bar, Planck's reduced constant. For field theories, it is the same idea. One takes the canonical momentum of the field theory, one takes the field itself, and one calculates the commutator, pi times phi minus phi times pi, and one gets a similar non-trivial commutator. In other words, pi and phi, the momentum of the field and the field itself, cannot be ordinary functions that commute. They do not commute. Now, this quantum mechanics, as many of you know, has been very successfully applied to electromagnetism, the weak nuclear force, and the strong nuclear force. Very successful theory, probably one of the most peculiar things that nature gives us, yet one of the most well-tested theories. In all its peculiarities, quantum mechanics performs extremely well. So, but what I didn't mention here, electromagnetism is here, weak nuclear is here, strong nuclear, that's chromodynamics is here. What about gravity? Gravity, as we said, is not a conventional force, if you believe in the paradigm of general relativity. The electroweak force, electromagnetism and weak force, and chromodynamics, the strong nuclear force, they are fields like photons that reside in space-time. You can ask where and when these things exist. Where does the photon exist? When did it exist? When was it absorbed? This makes sense for regular fields. We say that these fields propagate on a space-time, and the space-time gives you the where and the when. That's why it's called space-time. But gravitation, as described by general relativity and similar theories, is a theory of the space-time itself. It's a slightly different thing. It is not a field on space-time where you can say where and when. It is a theory of the where and the when. That's what gravitation is in the paradigm of general relativity. What you are trying to do when one is trying to quantize general relativity. In some sense, there are some differing opinions on this, but it seems to make sense that what one is trying to do is one is trying to quantize space and time itself, or maybe even something more fundamental. It may be that space and time make no sense at all in quantum gravity, and that space and time is a purely classical phenomenon, and at very high energies, it makes no sense to talk about space and time. Those commutators I talked about in the previous slide, these things here, they are usually, these are called equal time commutators. Does an equal time commutator even make sense in general relativity when you are actually quantizing the space and the time, or attempting to? These are all rather fundamental questions. Many of them do not actually have a very good answer yet. Here is just a picture, maybe not to be taken too seriously, but general relativity dictates what is your future, what is your present, and what is your past. So here is a picture of some curved surface, this grid here, that represents space-time that we live on. Over here, if you happen to be living here, your future is in this direction, this arrow that goes up and to the right. If you live here, your future is up in here, slightly more up and less to the right. And if you are out here, far away from what Mehdi called the throat, you have your future is up here. So general relativity dictates all of our futures. What is our future and what is our past and what is our present? And if you're trying to quantize this theory, then in some sense you are quantizing what is future, what is past, what is present. Again, a rather complicated and interesting issue. We can ignore these issues though. We can say, okay, yes, those are fundamental, but let's ignore it. Let us try to quantize gravity in the usual sense that people quantize other field theories. Then what do? You take this metric, which gives you the modified Pythagoras theorem of space-time, and you write it as this thing here, this eta. One writes it as, this is the metric of special relativity with no gravity. This is the relativistic Pythagoras theorem with no gravity. And then you look at gravity as perturbations on that metric. You change the metric of special relativity by order epsilon squared, more and more, depending on the precision you want. And so what you get then is you get a theory of H, this field H, propagating on a flat background. That's the theory that arises. You have special relativity with this H field, H1, or H1 plus H2 if you're going to higher order. But at first order, H1 is propagating on the flat space-time. All right, and then you try to quantize H1 like you do any field, electromagnetism, a strong, weak nuclear force, all of those good fields. We now quantize those. That's perfectly nice to try. But the problem is you pick up infinities. You pick up infinities when you try to make predictions from this theory. Now, in electromagnetism, these infinities can be tamed by a process called renormalization. Renormalization works very well because the fine structure constant of electromagnetism is unitless. But the coupling constant that arises, each of these terms has an epsilon, epsilon squared, epsilon cubed in it. The coupling constant, as we call it, epsilon, is not dimensionless here. It has units of length. So it's a bit complicated, but what it means is that at first order, you have to renormalize a certain way. You have to subtract the infinities. And the first order will not work in order. You need a new scheme to subtract the infinities at the second order. If you go to third order, you again need to introduce a new scheme to subtract the infinities. Unlike in electrodynamics, where one scheme tames all of the infinities. Electrodynamics, we say, is renormalizable, meaning you can get rid of the infinities in a consistent way. This type of naive quantization of gravity, you cannot get rid of the infinities that way. Here's an example of an infinity you get when you try to calculate, I believe this is an amplitude of graviton scattering. I don't remember exactly. But what happens in this expression at the bottom of the page here is that you do a Feynman expansion. Don't worry if you've not seen this, but it's basically you do these Feynman diagrams. This is the This is called a second order expression, this first one. The middle one with the one loop is fourth order expression. This one over here is 1, 2, 3, 4, 5, 6 order expression, or order is the number of connections in the diagram. So if you go to two loops, notice what you get. You've got, this is the Riemann curvature tensor we talked about earlier. It goes to the power of 3, essentially, of the Riemann curvature tensor, this expression. But the problem is we have this delta. And this is this calculation was done using what's called dimensional regularization, where one sets the space-time dimension as 4 plus or minus a certain amount. That certain amount is delta. And in the end, of course, we live in a 4-dimensional space-time. So after one does the calculation, one has to take delta equal to 0 to get back to 4 dimensions. So you see now when delta goes to 0, if the Riemann curvature tensor is not 0, you're going to pick up an infinity here. And remember, the Riemann curvature tensor is not 0 whenever you have gravitation. So this is the problem. It's you start picking up infinities again at the two-loop order. So what is a more promising way to do this? One can abandon that perturbative attempt at gravitation, and you can try to quantize the full space-time and not look at it as flat space plus a perturbation. There are many ways to do this. Many of them are called background independent methods, such as old Wheeler-DeWitt theory from the 60s. This has been supplanted by something we call loop quantum gravity. There are also rather fancy theories like causal sets and things of that nature, which I will not talk about today. But let us talk about the first two approaches, Wheeler-DeWitt and canonical loop quantum gravity. The way this works in the what we call the canonical approach, this, don't worry about it. This is the sort of the Pythagoras theorem of this approach. It's not important for this discussion. But what one does is one breaks down space and time into 3 spatial dimensions and 1 time dimension. The nice thing about this, the nice thing about general relativity and similar theories, it does not matter which time variable you pick. As long as it is a legitimate time variable, the theory works and makes good, appropriate predictions. So what we have is we have the 3 spatial dimensions, which I have drawn here as a flat sheet, but it actually could be curved, of course. Imagine that it's 3-dimensional, this sheet. And we look at this sheet evolving in some sort of time. And the points, of course, as you go from one time step to the next, the points can move. This point, for example, over time traverses over here. And that's basically the idea in these canonical approaches. You look at the 3 geometry, the 3-dimensional spatial geometries, as they evolve through time. And it's not wholly satisfactory, this approach, but it's a good start. So what I will look at first is, I will just summarize a few results here. Let's look at Wheeler-DeWitt cosmology. And the question then in this old Wheeler-DeWitt theory from the 1960s, is the Big Bang fixed? Well, there's this equation. It is called the Wheeler-DeWitt equation. Here's the wave function, the quantum mechanical wave function. This is the Hamiltonian of the matter field. Remember, there should be matter. And this here, this big expression in the square brackets on the left-hand side, this is, in some sense, the Hamiltonian of gravitation. These gammas here with the indices, these are the metrics, the Pythagoras theorem, on the sheets, on the 3-dimensional sheets. And it's some second order, not very well defined because you have a second order functional derivative. Mathematicians, of course, will tell you this is an ill-posed object, but one can try to naively treat it as a second derivative on the wave function with respect to the metric. And the question you can ask, or we can ask, is the Big Bang fixed? It's a bit ambiguous in Wheeler-DeWitt cosmology. It depends on the Euro-mechanics, of course, is open to many interpretations. Some people, such as the authors listed here, they say, yes, the Big Bang is fixed. And what we're looking at here is this is in some sense a parameterized plot of a quantity. Alpha controls tells you whether or not you have a Big Bang. How do you know you have a Big Bang? If alpha gets smaller, its magnitude gets smaller than a certain amount, you have a Big Bang. If alpha stays larger than a certain amount, and alpha is a parameter that occurs in this wave function, then you do not get a Big Bang. So in one interpretation by these four authors here on the left, they get an alpha which stays above the critical value. So they claim you do not get a Big Bang. In other words, the probability, because quantum mechanics is a probabilistic theory, the probability of having a metric with a Big Bang, they claim is 0. However, other people, using a slightly different interpretation and a slightly different method, they do get an alpha, which comes close enough to this critical point here, we'll call it, that one can say that there is a chance of a very high chance of getting a Big Bang. And they say that Wheeler-DeWitt cosmology does not cure the Big Bang issue. These are highly simplified models of the full theory, so one has to approach these results with a bit of caution. So in the Wheeler-DeWitt cosmology, whether or not there's an actual Big Bang, this infinite density start of the universe, is a little bit ambiguous. It's up for debate. Loop quantum gravity, similar theory of 3 + 1 in the canonical approach. The variables are different. There is A is called the connection. E is called the triad. E is kind of like the metric, the Pythagoras theorem. So if you see E in these equations, think about and these equations are not important, they're just to show you what they look like. E is kind of like the metric of before. This is called the Gauss constraint. It has to do with some injector constraint. And down here, this is the Hamiltonian or scalar constraint, the bottom one, which is kind of like the Wheeler-DeWitt equation that I showed you before. On the right-hand side, we have the matter Hamiltonian. On the left-hand side, it's the gravitational Hamiltonian. F is the field strength tensor. It's similar to the electromagnetic field strength tensor, just more complicated because it's what we call non-abelian valued. So one gauge fixes, one sets this thing, and you get a rather complicated set of, these are called constraint equations. What happens in loop quantum cosmology? Let's ask the same question. Is the Big Bang removed? This is one article of many that plots essentially, again in a highly simplified model, the wave function. And what this axis here, the v-axis, these are cells of a certain size in the space-time, in the universe. And if these cells shrink to 0 size, you have an infinitely dense region in the universe. If they do not shrink to 0 size, these cells, these volumes, then you do not have an infinitely dense universe. So this is look at this as sort of the like the probability versus the volume. This is a scalar field. The matter source was a simple scalar field. This axis that kind of goes in and out of the page. And if we take a look at this, so the question is, do the volumes go to 0 with any probability at all? Let me show you kind of a top view of this picture, slightly different, but a top view. Looks kind of like this. Here is the loop quantum gravity result, this red kind of parabola here. It is very difficult to see, I apologize, but you have the green lines, which are the classical general relativity results. And these green lines, one of them, it goes down to 0 here like that. And the other one goes up like the, sorry, well, this is the value of the scalar field. My apologies. This is over here on the left-hand side is the value of the scalar field. But what happens is that these two green lines, they go to the 0 axis. And that means if they go to the 0 axis, if we take a look at the bottom here, the volume, that means that the volume for those two green lines, I'm sorry, I've drawn on the picture now, it's hard to see. Let me try one thing. Very good. So these do go to 0, big two green lines, but the loop quantum gravity result, the red line, does not go to 0. That means the volumes do not shrink to 0 in loop quantum gravity, at least in this very simple picture. But in the classical general relativity, they do. One of these is the Big Bang, and the other one is called the big, I guess, sort of the or something like that. I believe that's basically what we're looking at. All right, you can also do an effective theory. And what an effective theory is within loop, and this is called loop quantum cosmology. What the effective theory is one has the classical theory, meaning the theory of general relativity applied to cosmology with Friedman equation and all those nice things. But one applies to those equations some corrections, some quantum corrections, which are inspired by loop quantum gravity. So the equations are not exactly the equations of general relativity. They are the equations of general relativity plus some corrections, which people think encode some of the effects of loop. Friedman equation gets modified. This is Hubble parameter, h squared. Kappa is 8 pi, and if you can put in the values of g, you'll have a g over c to the 4. Rho is the energy density in the proper frame. And what one has is the usual Friedman equation plus a correction, which goes as rho over rho star. Rho star is sometimes called the critical density in loop quantum cosmology. It's equal to this number in the middle of the slide, like that. So the density is bounded by the positivity of h squared. That means that rho cannot get too large. Otherwise, this equation can't be satisfied in the realm of the reals. So this is interpreted as saying that the loop quantum gravity correction prevents the density from going to infinity. In uncorrected classical gravity, the density diverges at the Big Bang. Here, it is in some sense protected. See at the top of this slide. So that's an indication that when one introduces some quantum gravity effects, then one gets a taming of the Big Bang singularity. There's no more infinity in the energy density of the material. Here is a plot of the scale factor. We have here is the red line is the loop quantum gravity or loop quantum cosmology in the effective theory prediction. And the dashed line is the uncorrected, meaning the standard general relativity result. The scale factor, A, which gives you basically the size of the volumes, of the volume elements in the universe. In the dashed line, it goes to 0. That means, of course, that the volumes go to 0. In the effective loop quantum cosmology plot, you can see, I hope you can see my drawings on the picture, A does not go to 0. So you do not get a 0 volume for the universe. One is plotting essentially the density of the universe, normalized, but the density. Notice that in the dashed lines, the density blows up to infinity. That's again the Big Bang. That's when everything gets squished together to infinite density. But in the purple or the pink line here, the red line, it is bounded. And that means if it is bounded, that means that you do not have an infinite density. And it's just normalized to 1 divided by rho max. So this is an interesting result. It seems that in loop quantum cosmology, at the very least in the simplified models that one is dealing with, that it's less ambiguous than the Wheeler-DeWitt quantum gravity theory, that one actually does get a taming of the singularity. Again, proceed with caution with these results. Let me now talk about black holes. That is the other place where we picked up infinities and they're relevant to astrophysics. Here are some pictures of black holes, but this is not of any great importance, but it's just to show you some schematics of what's going on. Here on the left-hand side, we have matter collapsing and it forms a singularity. And this right-hand side, we won't worry about this picture on the right-hand side. So Wheeler-DeWitt, they also studied quantum black holes. We also, some colleagues of mine and I, we studied black holes of various topologies, spherical topology, toroidal planar topology, higher genus topology. What we wound up doing is from the Wheeler-DeWitt equation, that equation I showed you with the 3 metrics with the 2 sheets, we managed to derive an eigenvalue problem. An eigenvalue, the eigenvalue gives us the 2 volumes. The 2 volumes, think of it as there's slightly more to it than this, but basically think of it as the area of the black holes. It's very roughly speaking, it's the area of the black holes. These eigenvalues derived from that Wheeler-DeWitt equation we found had to be discrete. And there was a quantum number, which we'll call n, which dictates what those areas are, those 2 volumes are. The larger the n, the larger the area of the black hole. So if one believes this simplified version of Wheeler-DeWitt theory that we used, then one gets discrete areas for the basically the two area of the black hole, the kind of like the surface area of the black hole. And what we plotted here is psi star psi. Psi star psi gives you the probability density. And what this plot is telling us, this is now a highly simplified, we had to simplify the problem a lot in order to get a tractable solution. This is psi star psi plotted as a function of time, okay? Because inside the black hole, what is important is the time variable. We have three cases. The higher genus case, black hole, is the solid curve. The genus 0 case is the dashed curve. The genus 0 case is the dotted curve. And then the remaining one is the dashed line. So we have three topologies. We have plane topology, spherical topology. We have toroidal topology, which is genus 1. And then we have higher genus case, which is all the higher genus cases, G greater than 1, can be treated all together. And this is the probability density. Now, what this graph is telling us, this graph is open to interpretation, but the way we've designed the problem, the most likely interpretation of this graph is that the bigger the value of this graph, the higher the probability that the classical metric, meaning the general relativity metric, accurately describes the space-time. So when these graphs are high, it is telling us that for those values of time, there is a high probability that the general relativity metric is a good metric to describe the space-time. When the value is low, this is telling us that there is a low probability that the classical general relativity metric is describing the metric of space-time. So this is for n equal to 1. This would be very, very small black hole. Here is n equal to 10. And if you make, which is a larger black hole in area, and if you make n larger and larger, this pattern gets more and more oscillatory over here. But let's look at what is happening over here. The singularity, the classical singularity, exists here at t equal to 0 on the left-hand side of this curve. What happens here? The probability, and remember what this is telling us, this is telling us the probability that the classical metric is valid for this value of time. Down here at t equal to 0, where classically one has the singularity, we get 0. That means that the classical metric, which is singular at the singularity, is maybe, this theory is telling us, is not valid at all at the singularity. And that would be good news, because of course that metric blows up, gives you infinite curvature. That's not a good thing. So this may be telling us that you cannot use the classical metric in the quantum theory at t equal to 0. Over here on the right-hand side, far away, we have a highly, this is far away from the singularity, we have a highly oscillatory case. This kind of looks like the particle in a box problem in quantum mechanics. And what one says in the particle in a box problem, one finds this in any textbook, introductory textbook in quantum mechanics. If you have an instrument of finite resolution, I will give the standard argument here, whether one likes it or not, it's up to one's personal taste. If you have an instrument, here we're talking about time, so the measurement is taken in finite time, then you are essentially measuring an expectation value of that over that time interval of these oscillations. And that means what you're measuring is the integrated probability over the resolution of your instrument. And so if you add up all of the probabilities over here, over a finite time interval, you will get a rather large probability if you add up many, many oscillations for large black holes. Remember, the larger the black hole, the more of these oscillations you will pick up in a finite time interval on the right-hand side. So that's why, at least our interpretation of it, is that for large black holes, which are expected to behave classically, if one measures, this is of course all inside the black hole, but let's pretend you are living inside the black hole, you would measure far away from the singularity, meaning at early time, you would measure, or at late time, actually late time is far away from the black hole because time runs backwards in this plot. You would measure the classical, you would have a high probability of measuring the classical metric. Close to the singularity, to the left, I will just repeat, very low probability of measuring the classical metric. Far away, with a finite-sized instrument, you would have high probability of measuring the classical metric. I should have plotted maybe n equal 100, but then the plot gets a little bit too messy. Here are the two plots, again, just for your comparison. The low black hole is very quantum in nature, not very much of a classical type of behavior. The large area, which is on the right plot, far away from the singularity over here, where, again, I hope you can see my red line that I'm drawing, you get very classical, at least sort of classical type of behavior, similar analogy to the particle in a box in quantum mechanics. And this behavior gets more and more classical, so to speak, as n gets large. And n, remember, tells you the area of the black hole. Okay, we can also look at black holes. We did in loop quantum gravity. Here we go to an effective theory. We're not now going to talk about wave functions, but we're going to talk about the classical theory, which is general relativity, but general relativity written in the connection variables of loop quantum gravity. And we're going to correct the theory applying some loop quantum gravity corrections. So we have a classical theory, it's going to have classical Hamiltonian, and we're going to correct that Hamiltonian of general relativity by applying some loop quantum gravity corrections. Here's the metric, the Pythagoras theorem, but written in loop quantum gravity variables. Again, we do it for various topologies. We have this d sigma squared on the far right. If this d sigma squared has this top value here in the middle of the page, we're talking about a spherical black hole, probably the most relevant in astrophysics. If it has, oh, my apologies. If it has this form here, the middle form, d sigma squared, we are talking about cylindrical or toroidal black hole. If it has the form at the very bottom here, we are talking about hyperbolic, which is compatible with higher genus black holes. What is of greatest importance for what I will talk about, and I'm almost finished, I won't keep you too long, is this function E3. If this function E3, right here on the far right-hand side of our modified Pythagoras theorem, if this function E3 goes to 0, the proper area of the two-dimensional subspaces goes to 0. In other words, the two volumes go to 0. If the two volumes go to 0, it turns out that the Riemann curvature tensor, we talked about that a little bit earlier, the Riemann curvature tensor, when projected in the orthonormal frame, will blow up. And that means you have infinite gravitational effects, and that's bad news. That's the singularity that we talked about earlier. So in the classical theory, in general relativity, inside a black hole, in reasonable black holes, E3 will eventually go to 0 for these types of black holes. Let's see what happens in the quantum corrected case. Here I'm just describing what I said about E3. We're going to now take a look at, these are called holonomy corrections, what we are going to apply to the Hamiltonian here. I'm just going to show you the results. Here is E3. This is the quantum case. It goes down. It looks like it's going to 0. But if one looks very, very carefully here, and one can do this function E3 on this first plot, plot A, is not going to 0. In fact, you can evolve it beyond 0 into negative time. And you can see here, for example, time equals negative 100, negative 200, negative 350 on plot B. You see that E3, again, it gets close to 0, but it never goes to 0. In fact, we can go all the way out to time equal minus 1 times 10 to the 8. And you can keep going. And you get these oscillations, and they smooth out. This, I'm looking at plot C now. You get these oscillations in E3. And that means you get a bouncing universe. The universe is kind of bouncing like it's kind of vibrating over large time scales. But the size of the universe never shrinks to 0. These other plots are not really that important. It's plots A, B, and C, which are of the greatest importance. And we can extend this to as far back in negative time as you want. So you get a new universe on the other side of t equal to 0. Instead of a big bang or a big crunch, or here would be the black hole singularity, which is like a big crunch, you get another universe. You smoothly go through the classical singular point because it is no longer singular, and you get this kind of slightly oscillating universe. What we are looking here is the Schwarzschild de Sitter black hole, which is the spherical black hole with a positive cosmological constant. Here's a similar set of plots for the Schwarzschild anti-de Sitter black hole, which is the black hole, Schwarzschild spherical black hole with a negative cosmological constant. Again, we smoothly go through the classical singular point, as you can see in graph A. Although E3 looks like it goes to 0, a close inspection shows it does not go to 0. And we can evolve. You can look in plot B if you'd like, if I could draw your attention to plot B. We can plot for negative values of time, again, at around t equal to negative 150. On plot B, it looks like it goes to 0, but it actually does not. And for large negative time, in plot C, again, we're plotting minus 1 times 10 to the 8. For example, long time, you do not get zeros. Even though the graph looks like it goes close to 0, one can inspect these points where it goes close to 0, but it does not actually go to 0. And you get this sort of slowly oscillating universe. And the oscillations have larger and larger periods, and eventually it settles down. So again, the black hole, the universe inside the black hole, I'm only talking inside the black hole, shrinks. But it never goes to 0 size. And then it starts to oscillate on the other side of the classical singular point. Here's the toroidal black hole. Very similar picture, but slightly different. Again, the graphs to look at are A, B, and C. Those are the plot of E3. E3 gets small, but not 0. We plot it here. We can evolve it to the other side of T0. And you get these oscillations again in plot C. They're slightly different looking for the toroidal case, but you get this universe of finite size. So you can go through the singular point of the black hole because it is no longer singular. This is the toroidal case. Here is the higher genus case. This is a very messy curve C. To be honest, with curve C, I'm not very good at numerics. I didn't do this, but I'm not a numerical person. So I cannot tell you whether this is numerical noise or they are genuine oscillations of the universe. But let's look at plot A. Again, plot A, the size of the universe as time progresses in the black hole goes to close to 0, but it doesn't become 0. And then it starts expanding a little bit. And then it will start oscillating over here to the far left, which I did not show. But you can see later on, here's E3 in plot B at a time of about minus 255. And you can see the oscillation start. The reason I plotted at minus 255 is that's where the oscillations start in the universe beyond the classical singularity. And over here, we're going to minus 10,000 in plot C. And again, you can see E3 is never 0, but it does oscillate wildly. And again, I do not know if this is numerical noise. We tried to control the numerical noise as much as possible, but this was not, the focus wasn't on numerics. So we get this sort of value of an oscillating universe. So no singularity in any case, and all of them produce. After you fall in the black hole, you will go towards the classical singularity, but in the quantum corrected case, it is not singular. You do not get an infinite density. Instead, you pop out into an oscillatory universe. That's the picture that arises here in the loop quantum corrected black hole if you go inside the black hole. Let me then summarize and end here, and I thank you for your attention. Let me just read what is on this slide. General relativity is still arguably the best out of all the theories of gravity that we have. It is a wonderful theory, general relativity, in my opinion. But there is something called diffeomorphism invariance. This is that idea that general relativity is not a regular field theory, but it is a field theory of the space and the time on which all other fields propagate. This is called diffeomorphism invariance, sometimes called background independence. This fact makes general relativity very difficult to quantize, even at a conceptual level. What is it that we are quantizing when we are quantizing general relativity? Nobody really knows what it means to quantize space and time. There are some background independent quantizations which try to respect this diffeomorphism invariance. One of them was the old Wheeler-DeWitt theory. This has been supplanted by the newer loop quantum gravity theory, and there are others like we mentioned, causal set theory and things of that nature. The Wheeler-DeWitt theory is ambiguous about the Big Bang singularity, as I mentioned, depending on interpretation. Our black hole work that I showed you earlier seems to indicate that the classical metric, the metric which goes singular, maybe is not valid at the Big Bang, but we didn't study cosmology for that. We did black holes. For black holes, that's what we seem to get, that maybe the classical metric should not be trusted near the singularity, which would be a good thing. In loop quantum gravity, the singularity of the Big Bang seems to be removed in all cases. for loop quantum cosmology and similar studies with effective wave functions, which is a bit more fundamental than the effective theory. We did the effective theory for black holes. Those are those oscillatory graphs that were shown just recently. And it seems to show that for black holes, the singularity is removed and replaced by some sort of bounce into a different universe that oscillates. Again, a word of caution, none of these results are fully robust, because none of these results are in the full quantum gravity theory. In fact, the full quantum gravity theory in loop quantum gravity does not actually exist yet, but people are working on it. So to answer the big question, this is, I think, the biggest question. Do we actually need quantum gravity? That is up to you. We certainly do not need it to design buildings, aircrafts, roads, or bridges. Newtonian gravity is very good for that. We generally do not need it to design space probes or study the solar system, unless you want super high precision. We do not need it to study most of stellar structure or galactic evolution. Nor do we need it to study much of cosmology beyond 10 to the minus 43 seconds. Actually, we do not need it for any of this, quantum gravity. You do need general relativity, though, for some of these things, but you do not need quantum gravity for these things. You do need it, though, or at least we think we should need it, if you wish to study what happened 10 to the 43 seconds or earlier after the classical Big Bang. You do need it to understand what is happening inside black holes. Otherwise, you're stuck with a singularity. And if you wish to reconcile how particles, which are fundamentally quantum in nature, affect the space-time, in other words, how do quantum particles gravitate, we do need that thing. Okay, good. I think we're just right on time, so I will end here. I would like to thank the organizers of this conference, as well as New Alipur College, for inviting me to speak. It was my pleasure to speak to you all. Thank you very much.
Thank you, Andrew, for your nice presentation. So question, comments? Okay, already I can see some questions. What type of renormalization has been used to remove divergences in quantum gravity?
Oh, yes. Usually the standard ones, dimensional regularization, effective actions with counter terms in the action. Many things have been used, but of course they all, because they're all just different guises of the same thing, one runs into the same problem. If you're trying to renormalize an effective action by adding counter terms, you have to add an infinite number of counter terms, because at higher loop order, you pick up different types of infinities. So all the standard techniques of quantum field theory have been used, but the divergence is quite real. In string theory, which is not a background independent approach. Oh, sir? Yes?
Another question. What's about feedback from?
Oh, sorry, I don't understand. Feedback?
Yes, are you also doing feedback form?
Oh, I apologize. I don't understand the.
It is not clear to me. Okay.
In due course of time.
Okay.
Okay. Thank you. Thank you.
Any other question?
Okay. Yes, I see a question about the string theory. Yes. So
you want to speak on it?
Yes, this is actually related. Thank you. This is actually related to the previous question about renormalization. In string theory, when one has these, I don't know if I can do it very quickly. Really slow. Yes, right here. If you can see, I don't know if you can still see my presentation, but on the lower right, there are these diagrams. In string theory, these get replaced by diagrams which do not have lines, but they have sheets or tubes. And the infinities which arise in quantum field theory, they arise at these vertices where the lines connect usually, and the integral over the momenta, the interior momenta, and that's because you get these sort of delta functions which are ill-behaved. In string theory, the lines are replaced by tubes, so you get sheets. And it turns out that at the vertices of these diagrams, you do not get these delta functions, but you get something that is proportional to the Euler characteristic of the surface that forms when the sheets connect. And that's much better behaved. And so that tends to tame in infinities. But to be perfectly honest, although string theory has been proven to be more finite than the standard approach, it is still up for debate whether string theory at all levels is perfectly finite. But it is a very interesting and promising approach. But then you have the issue of background independence, which people are also trying to address in string theory. But in the normal way of studying string theory, one doesn't have the background independence.
Okay, let me see if there is. Is it right that quantum gravity does not describe the existence of Big Bang theorem?
This seems to be the case. As we mentioned in Wheeler-DeWitt theory, in a simplified form of Wheeler-DeWitt theory, the Big Bang is slightly ambiguous, but in a simplified version of loop quantum gravity, it seems that the Big Bang is removed. Again, I am sure that because these are not fully formulated yet, we can probably find arguments one way or the other, but it seems to be that statement is correct, that the Big Bang is most likely eliminated, as is the black hole singularity.
Okay, another question. Can quantum gravity be applied to understand the black holes?
Right here. This is in Wheeler-DeWitt theory. The fact that we have a 0 in this plot at the origin means that there's a good chance that the Big Bang, that the black hole singularity is eliminated. And in these graphs at the end here, the fact that the E3 graphs do not go to 0 is an indication that the black hole singularity is eliminated, and you get a new universe, so to speak, on the other side.
Okay, if there is no other question, let us thank the speaker. And
thank you very much. It was my pleasure. Thank you.
Our next speaker is Shahjahan Molla. Yeah, he does not need any introduction to the audience because he is from the New Alipur College. So Shahjahan, get ready with your presentation.
Yes, sir.
Are you ready?
Yes, sir.
And Mehdi will take over the chair.
Okay, sir.
Thank you.
Shahjahan, start your presentation.
Yes, sir. Sir, my slide is seen?
Yes, you can proceed.
Okay. Good evening, everybody. Today I want to discuss about the dark matter emit pulsar property, and I want to give the basic idea about the star. At the starting, what is star? Star is a luminous fixed point in the night sky, which is a large, and it is remote radiant body like our sun. And in the star, we have already known the plasma, it is held together by its own gravity, and interior it always hydrogen is converted to the helium, and due to nuclear reaction always electromagnetic radiation is coming out from the star. And I want to give the concept of compact star. What it mean by compact? Compact means high mass, small radius. That means density is very much high. And the collectively star, which are basically known as compact star, is either white dwarf or neutron star, and which neutron star are rotating are known as pulsar. I want to give some pioneer work on compact star model previously. In 1916, Einstein first gave his field equation, and then in 1939 he has theoretically shows that Tolman, Oppenheimer, and Volkov, they have shows that the a fluid will be in stable equilibrium under the force of gravitational and hydrostatic force. And if we consider anisotropic model, the sphere will be held together equilibrium under gravitational force, hydrostatic force, and anisotropic force. And then in 1959, Buchdal shows that if for a fluid sphere, mass to radius ratio should be less than equal to 4/9. And thereafter, in 1964, Chandrasekhar shows that for a dynamical stability of a fluid sphere must be required, the adiabatic index should be greater than equal to 4/3. And then in 1992, the cracking condition given by the Herrera. That means a fluid sphere should be stable when the sound velocity or sound speed inside it less than equal to 1. Since we give a stellar model, or anyone can give a stellar model, by the stellar model, what we want to find out? We want to measure by the model the density and pressure inside the star as well as pulsar, and its mass, its compactness, redshift, and probable radius of the star or pulsar. For a standard star model or pulsar model, anyone can give, but some criteria should be fulfilled. What is the criteria? At the center, density and pressure should be maximum, and density and pressure monotonically decreasing toward the boundary or the surface of the fluid sphere, that means star surface, and pressure should be 0 at the surface of the star. And the star should be satisfied TOV equation, that means Oppenheimer-Volkov equation. And in the star, sound velocity or sound speed should be less than equal to 1. And this star model also satisfies mass radius ratio m/r should be less than equal to 4/9. And I want to give the idea about the dark matter admit pulsar. Previously, Dr. Debadesh Bandyopadhyay already briefly discussed about the pulsar, and then my supervisor, Dr. Mehdi Kalam, also discussed about briefly the dark matter and its property. And in this study, we have taken a two-fluid model in the consider of SIS dark matter density profile. And here we give the basic idea about the 4 pulsar which are taken for 4 different galaxies, and they are stay in the spiral galaxy. And in this calculated the basic parameter in our model, probable radius, compactness, surface redshift of the 4 pulsar. And in this study, we have taken the Einstein field equation. Here I have shown. In equation number 1, if we have taken the Einstein field equation, we get if we take the metric in this form for a spherical symmetric metric fluid sphere, since star or pulsar is a fluid sphere, we get equation 2, 3, and 4 for Einstein field equation. Here, equation number 3 and 4 are arises due to we have taken anisotropic model here. And for the solving of Einstein field equation 2, 3, and 4, we have taken Hinzman metric, and Hinzman coefficient are taken e to the power nu this function and e to the power minus lambda this function. And we also consider for energy momentum tensor in this form, minus rho PR PT. Here rho is the density, PR radial pressure, and PT is the transverse pressure. And here we have introduced the SIS model in our pulsar model, where SIS model dark matter density profile is considered K by 2 pi g r square, where K is the velocity dispersion. And this density, dark matter density, is related to the pressure like m into K by 2 pi g into r square, where m is a constant. Now, this velocity dispersion K is calculated or related from the halo velocity, which is calculated from the transverse velocity of the galaxy. And this velocity we have taken in our study, which are already reported by observational data, which shown in the table 1, where K is the velocity dispersion value. This value we have taken in our calculation, and this K is putting in the field equation by the form. The effective density is denoted by normal matter density plus dark matter density, and effective pressure is denoted by normal matter pressure and dark matter pressure. Therefore, when we adding dark matter with normal matter, we have got the Einstein field equation this form: density this form, pressure this form, radial pressure this form, and transverse pressure this form. And in our calculation, we have taken K value 10 to the power minus 8 for spiral galaxy. And in this calculation, or in our study, we have taken metric coefficient A this value and C this value, and here constant M equal to 10 to the power minus 6. Such that we have chosen such parameter value that the pressure must be vanished or zero at the surface of the pulsar. Here, from the Einstein field equation, if we putting all the metric parameter, the velocity dispersion value K and constant M in the Einstein field equation, we have got the density function this figure, and pressure, radial pressure this figure, and transverse pressure this figure. And this is the anisotropy parameter, that means delta, that is indicate PT minus PR. Here from the figure it is clear that density and pressure at the center is maximum, and they are monotonically decreasing toward the surface or the boundary, and pressure goes to zero on the surface of the star. And in this study we have existing ordinary matter and dark matter, yes or not. In this case, we have all conditions that the real matter is existing inside the pulsar. Here we check null energy condition, weak energy condition, strong energy condition, and dominant energy condition. And we have got all the values from our calculation, and which are plotted in the figure. And we have seen that all the value, density, pressure required for null energy condition, weak energy condition, strong energy condition, and dominant energy condition is satisfied in our figure. And in this model, we also check the matching condition, which is required for, very much required for a standard stable star model or pulsar model, that in our model is applicable to the inside the pulsar, but outside the pulsar or the star, we have used the Schwarzschild exterior matrix. Now at the boundary, that means R equal to V, where side metric we match to the external Schwarzschild exterior metric. And when our metric is compared to the coefficient of dt square dr square, we got the compactness factor of the pulsar dash form, where m is the mass of radius of the pulsar. And in this pulsar model, dark matter atomic pulsar model, we also check whether TOV equation is satisfied in our model, yes or not. We have know that for a standard stable star model, since star is a hydrostatic equilibrium, gravitational force, and anisotropic force, all the three forces sum should be equal to 0. And the value of Fg, Fh, and Fa are plotting in the figure, and we have see that all the three forces counterbalance to each other, and our model is satisfy standard star model. Here, already since before I have already told for a standard star model should be satisfied inside the star, velocity of sound should be less than equal to 1, and which is a cracking condition. And here we see that radial velocity is less than 1, and this velocity, radial velocity calculate from dp by dr. dp mean this calculate from the pressure, and d rho is calculated from density, and when we divide dp by d rho, we got the velocity square, and we have plotted here, and we see that radial velocity is less than 1, and transverse velocity also less than 1. And since we have taken anisotropic model here for a stable potential region, the magnitude of velocity square difference should be less than also 1. Here we have shown that Vt square minus Vr square is less than equal to 4 by 3. That means 1.44 required. Here our pulsar model give above 2.5. Pulsar model is stable. And from our model, we have function which is calculated 4 pi r square dr rho, where rho is the effective density. Already I have told rho effective mean rho plus rho d, where rho is the normal matter, rho d is the dark matter. And when we put in this equation, we have get the such result. And when all the metric parameter are putting in this equation, we have got the mass function graph here. And we have also calculated compactness U equal to m by v, mass by radius here, and we are plotting here, and we have got such figure, and we have seen that compactness value at the boundary is less than 0.35. That means this model also satisfies Buchdahl condition. Buchdahl condition requires less than equal to 4 by 9. We have also calculated surface redshifting from our model, and where redshift is Zs, and this Zs is related to the compactness U, such as Zs equal to 1 minus 2 power minus a minus 1. And when we are putting all the metric parameter in this equation, we have got the figure here, and from this figure, any radial value, we have got the surface redshifting of the pulsar model. And in this study, we have taken 4 pulsar, namely J1714, 2021V, and similar for another 3 pulsar. And from the mass function graph, here we have shown in the figure, and this green region is shows reported mass region, and from this reported mass region is cut or touch the mass function graph at the 2 point, and from this graph we have calculated the probable radius of the pulsar. And when the probable radius of a pulsar is find out for pulsar, we have got the result we have got the result here. The radius of the pulsar from our model, such value, compactness this value, and redshift this value. Therefore, from our model, we have got the pulsar which are made of ordinary matter admixed with dark matter. We have got the radius, compactness, and redshift from our model. Therefore, we have studied the physical property of the four mentioned pulsar located in the four different galaxy region, and they are satisfy all the stellar condition, and we have find out their basic property, that means their radius, compactness, and redshift in our study. Thank you.
Thank you, Shajan, for your wonderful talk. So, from the audience, any questions? I think no questions is there. Yes. Yes, sir.
Yes, now about the vote of thanks.
Oh, I see. Okay.
Yeah.
Okay, we give the vote of thanks. Okay.
Yes, sir. Let me thank the principal of New Alipur College, Dr. Joydeep Sarangi, Vice Principal, Professor Divesh Bera, and IQAC convener, Dr. Samavrato, for their encouragement and assistance for this webinar. Let me thank Professor Kembhavi for his beautiful speech. We know he is a very busy person, but he was kind enough to find the time for this webinar. Let me thank Professor Andrew D. Bennett for his beautiful speech in this webinar. We know that it is early morning in his country, but he somewhat tried his best to attend the meeting. Let me thank Professor Devadesh Bandyopadhyay for his interesting lecture on neutron star and for his conducting today's session. Very special thanks to Professor Mehdi Kalam sir for all that he has done for this webinar. From the very beginning, he was a part of it, and in every sphere, he helped us. He had given a very interesting lecture on the wormhole and presided over the previous day's session. Thank you, sir. Let me thank the staff of the Department of Physics who gave their 100% for the success of this webinar. Let me thank the present students and the alumni for their spreading of the webinar news through social media with much enthusiasm. Let me thank the participants from other departments from this college and other colleges also to make the webinar a grand success. I hope they are satisfied for their valuable time they have spent on it. Thank you.
Thank you very much. So Professor Bhaskar Bhattacharya, you declare the.
Actually, we declared the webinar to conclude here. Thank you for everything that you have done and the participants also. Thank
Master
you.
sir, sir,
Yeah. Yes.
in the chat box feedback from all the candidates should be fill up you mentioned.
Yes, actually, I have circulated the form link in the chat box. Karthik has done it, and then I have done it twice. I think everyone has received this link, and they are required to fill the feedback form of the certificate.
Okay, sir.
Thank you, everyone. Let the webinar be concluded.
Yeah.
Shajan sir,
Okay.
I will share it again in all participants' email ID. So don't need to worry.
Okay.
Andrew. Yes. Thank you very much for your wonderful talk. Yeah. Andrew,
Yes.
are you hear me, Andrew?
Sorry, it was my microphone. I'm sorry. Thank you very much. It was an honor. It was a pleasure to speak. Thank you.
You
Thank you,
delivered
sir.
a wonderful, wonderful talk.
Thank you. I keep forgetting to turn on my microphone. My apologies.
Oh, I see, I see. Okay, okay, okay. Thank you. See you next time.
Thank you very much.
Okay. Devadass sir?
I think Devadass sir has left this meeting.